Yeah. So as I was trying to recollect representation, then so representation. So the representation then is you can think of it as a free abelian group over irreducible representations of G, or you can think of it as a ring of all, so free abelian group over all G representation and go mod these kind of relations. Yeah, V plus W minus V plus W. So in general, what people do is you go mod relations V. Yeah, so you go mod relations. So if you have a short exact sequence V1, V2, V3, then you go mod relation V2, V2, the class of V2 minus class of V1, class of V3. Yeah, but here since we know that if as soon as you have a short exact sequence, you have a splitting. Yeah. So G representations, the category of is, in other words, the category of G representations are semi-simple. Okay. So in this case, this is good enough. Okay. So this isomorphism that this is same as free abelian group over irreducible representation follow from the fact from the complete reducibility. Yeah, so every representation you can write it as direct sum of irreducible representation. From there, it will follow that these two are isomorphic. Okay, so now and then we saw that this of course addition is clear. I mean that because it is a free abelian group. The multiplication is given by tensor product, extending tensor product linearly for sums, and this makes RG into a commutative ring with unity, where unity is the trivial representation. Okay. So another way of thinking about so and we have this character function. Yeah. So elements of RG are called virtual representation, and we have this for ordinary for representation, we know what the character is, and for other representations, so for other elements of RG, what you do is use this formula. Yeah. So summation AI VI is this. Summation AI chi VI. So this will sort of agree because of the formulas for character function. Yeah. So so we know that character of V plus V prime is same as character of V plus character of V prime. So from there it follows that this is a well-defined map, and it's a ring homomorphism. Yeah. And in fact, it is the fact that the characters determine the representation tells us that chi is an injective ring homomorphism. Yeah. And the image, so you can also identify RG as image of chi, yeah, because it's injective. So it is an injective ring homomorphism. So the image of chi is isomorphic to RG, which image of chi in the class of G. So that set we had called virtual characters. Yeah. So you can think of representation ring as ring of virtual characters as well. Yeah, by this identification that representation is determined by the character. So that's another way of thinking about representation. Okay. So, so in other words, you can we can think of RG as linear combinations of irreducible characters, yeah, with component-wise multiplication. That's another way of thinking about RG. So they are all isomorphic and natural identifications and so. Okay. So that then we saw a few other things, but I'll not go into it. You can just look at that lecture. But there are a couple things which we didn't do. So if H is a subgroup of G, then we have two homomorphisms, two maps. One is the restriction map from Rg to Rh. So this will be a ring homomorphism. This is a ring homomorphism, and we have the map, and we have a map from Rh to Rg as well, which is the induced map. Yeah. So so given a representation, you can do the induced representation, or given a character, you can do a induced character. Yeah, so in fact, int was defined when we were trying to do the define in yeah. So for any class function, we had defined the int of that class function when we were trying to write down the character for the induced representation. I think around that time. So. So we see that, but remember, int has no chance of being a ring homomorphism. Yeah, this is just a group homomorphism. Why is int not a group ring homomorphism?
Int of tensor will not be the tensor reference.
Yeah, but why? So
like there are like we can use a dimension argument over there.
Yeah, so even the dimensions don't match, right? So if you take, for instance, trivial representation, even so trivial representation, V is a trivial representation, then V is equal to V tensor V. Yeah, but if you do int of V, then you'll get the dimension will be the index of G in H, index of H in G. On one side, and but if you do for this induced representation, so on one side you'll get this as the dimension, on the other side you'll get square of this as the dimension. Yeah, so it won't match. So even the dimensions don't match. But of course, res is indeed a ring homomorphism, because the restriction is basically restricting the function, if you like, yeah. Or we know that tensor restriction behaves well with tensor product. But if you think in terms of function, it is clear that it behaves well with respect to multiple. Yeah? So maybe just note this is restriction of the function of the function class function, let's say. Yeah, so you think of it as on virtual characters. So they are all class function. You're just restricting it, which of course behaves well with respect to addition and multiplication. But the end is more common. So the induced character is a complicated formula. Yeah, you have to consider all the conjugates of G. So if you want to evaluate in the chi at some element of G, then you will have to conjugate that and see what all lies in H, and then take the average of those values. Yeah, that is how the int representation int character was computed. So it's more complicated, but the addition part is okay. So so int is a group homomorphism, since so that just follows from the fact that sum of int of V plus V prime is isomorphic to int of V. So this we saw when the first statement we saw when we defined it. Yeah, the same as, so from here it follows that this is a group homomorphism. Yeah. So this is straightforward observation. And another observation is that if you have a field or even a ring, and you tensor both sides, then they still remain a linear map. Yeah. So let A be a ring. Then, so we'll mostly be thinking in terms of field. Yeah. So Q or C. Then A tensor less from RG. So RG, remember, is a Z module. So you can, and any ring is a Z module. Yeah. You just, just give a ring homomorphism from C to A, sending one to A be a commutative ring with unity. Maybe I should. Commutative ring with unity. So normally in an algebra course, this is my standard assumption without saying, but since we are doing representation theory, where most of the things we'll see are non-commutative, it's important to spell. So this to RH tensor A and A tensor int from RH tensor A. So I'll drop Z. Yeah, there's no other way to think of it. So the tensor is over Z. Are linear maps. Okay. So here all the rings are commutative, so there's nothing deep here. Okay. So so this is the setup. This second part we only need in the proof, not really. So I'll now state Artin's theorem, which is a statement about the induced represent in this end map. Yeah. So let me Artin's theorem. Let X be a subset, be a collection of subgroups of, so not all subgroups, but some subgroups, be a collection of subgroups of a group G. Okay. And then the following are equivalent. The following are equivalent. G is the union of conjugates of all elements of X. Yeah, union of conjugates of all elements of X. You consider union over so maybe just one union. G in G, H in X, G inverse H G. This is should be equal to G. Yeah. That is what symbolically it means. And 2, this map, the map so you have the end map, yeah, end from RH to RG, yeah, for maybe, yeah, so this is let's call this phi, yeah, because so this is for one h in G in X, but we can do this for all h, yeah, so h in X. So for all, so for every h in X, we have this end map, and in GH. So for every h, so you get a map from the direct sum as well. Yeah, so you just take the direct sum of each of these in GH. So that is what we are calling phi. Yeah. So on the map phi, so this is union. The union is whole of G is equivalent to saying that the map phi is almost surjective. So meaning, that means the image is in the map, and the map phi has co-kernel, finite co-kernel. So the image is going to be a finite index subgroup of RG. Yeah, he has finite co-kernel. RG mod phi, image phi is finite. It's finite. So I'm just saying what finite co-kernel means. Yeah, it's a finite group. Okay, and so another way to interpret 2 is that so which there he labels it at 2 prime, so I'll also label it as 2 prime. So this is all from SER, yeah. So another way to say this is that if I take a character of G, then that character, maybe we can't write it as some integer linear combination of character of H, but what we can do is that some multiple of it, some scalar multiple of it is indeed some linear combination of this. Yeah, so in other words, let chi be a character of G, so character of some representation of G. And then there exists I can't write. Then there exists D such greater than 0. So I don't want to make it 0. Greater than 0 such that D times chi. So chi may not be, but if you tensor it enough, then D times chi is summation chi hi, chi h. So h in x. No, not this, but we have to do the induced thing. Yeah. And th chi h, where chi h is some characters of h. So any character of G, you can write it as some sums of some character of H. So that is because you what. So it is equivalent to 2 because if I take any character of G, then these are all finitely generated. So there since this is a finite group, I take D. So there will be some D such that D times that character will lie in will become 0 in this co-kernel. Yeah, which means D times that chi will become will be in the image of phi, which precisely means that this happens. Yeah. Okay. So in so in fact it's true for virtual characters, but in particular for characters. Okay. So 2 and 2 prime are basically the same statement. So the non-trivial part is that this characterizes the fact that this generates G. Yeah, not generates. The union is whole of G. So one concept corollary is so one has to find out what kind of sets have these properties. So what kind of collection of groups, subgroups have this property. So for instance, cyclic groups do have it. Yeah. So I mean, given any element in G, you consider the cyclic group generated by G, and then of course their unions are going to be a whole of G. Yeah. So the observation, let X be all cyclic subgroups of G. And then X satisfies 1. Satisfies 1. Hence, what you can say is that any character of G is induced from is a linear combination of induced character from cyclic subgroups of G. Characters of G is not every but some power, not every character, but you have to multiply that character by D. So you can say that is Q linear. Yeah. So up to division by D, it is true. Yeah. So Q linear combination, but D you don't know. Actually, so there is one proof where one can show that D is same as size of G. Okay.
Excuse me.
Yeah.
So over here in 2 prime, are chi h any character or virtual characters for you?
So if you start with character, then this chi h will be a character.
Okay. So I
Yeah.
was thinking, can like just mind, can kh be zero here as well? Otherwise, it's not clear to me why 2 and 2 prime should be equivalent. Like it's just in the image, right? So there might be some things are being mapped to zero or something like that.
Yeah, so chi is a character of G. Yeah, so there is a bit of a argument needed. Yeah. So mm, yeah, but yeah, so D times chi is a character of G, and yeah, so if yeah, so what do you do? So you can, yeah, so maybe you yeah, so you decompose it. So it is, if D times chi is character, then you think of it as direct sum of irreducible characters. Yeah.
Yes, sir.
So or maybe yeah. So what? Yeah. So the point is all the coefficient. Yeah. So all the coefficients are positive. Yeah. So if you write it as direct sum of irreducible characters, because it's actually a representation, not some virtual representation. Yeah. So now if you consider, yeah. So yeah. So this. Yeah. So yeah. So yeah. So from there it should follow. Yeah. So this end. Yeah. So yeah. So if there are some yeah. So suppose it is yeah. So maybe this is how one can do. Yeah. So if chi h is a virtual character, you can write it as chi h plus minus chi h minus. Yeah. And then show that this you can throw away the chi h minus, because that is, so if you do the end of it, then this will still be negative. Yeah. And this will be positive, but the end result is should be all positive. Yeah. So there can't be any negative component. Okay.
Yes.
So that is how.
So
So the map, the cone maps to the cone. Yeah.
yes, sir.
Yeah. So that is what.
Yes, sir.
Okay.
Just about this, we are like there are virtual characters where chi plus and chi minus both are zero. For example, chi being zero, and so on. So I allow chi to be zero, and then in the hg chi is zero.
Chi h can be zero. Chi h is a so the zero character is not a virtual character. It is a character. It is the representation of the zero representation. Yeah, when the vector space is zero.
Okay, so we are assuming that, like we are not assuming v is non-zero. Okay, so then it's clear. Then it's clear.
Yeah, v zero, the vector space, zero vector space is a representation. That's not a problem. Yeah?
Okay, so yes, actually that was where I was stuck. Yes.
Okay.
Yes,
Yeah. So then there is no issues, right?
Yes, no, then there is no issue.
Okay.
Yes,
Okay. You're welcome. So so every character of G is a Q-linear combination of induced of every character or representation also we can yeah. So maybe to make it sound more representation. Yeah, maybe since I'm writing Q-linear, it's better to write character. Character of G is a Q-linear combination of induced character induced character from cyclic subgroups of G. Subgroups of G. Yeah. So this is immediate from this star and 2 prime. Yeah. So yeah. Yeah. So yeah. So maybe yeah. I'm planning to do the proof next time. Yeah. So maybe I mean the proof is not very long, but it's not that bad, but anyway, so since there is plenty of time, I'll do the proof next time. Okay. So so maybe I'll stop here, and so it will be a shorter class today. But if you have some questions or comments, you can ask me.